Okay, so welcome to the details portion of the talk. So we're trying to control the volume of this locus where you have two short independent saddle connections. So I'm going to explain first the heuristic that suggests why this should be true. And then I'll describe kind of some issues with this heuristic, and then I'll say how to overcome the issues. So the heuristic, which was similar to the heuristic, I mean, for the very the thing that I said for the case where you just have one saddle connection. So each SI gives a factor. So you can be sort of part of a basis for the relative homology, and then since the saddle connection SI has length at most epsilon I, it gives a factor of epsilon I squared, since the period, the vector giving its length and direction, lies in the ball of radius epsilon I, which has area volume pi times epsilon I squared. So, but then, so like we kind of think of, so the measure, this is an affine measure, so it's basically a Lebesgue measure in some sort of coordinate system. And so we wanted, these SIs should be part of that coordinate system, but then there are a bunch of other coordinates. So then the hope is that all the other coordinates are bounded. So then you'd have like epsilon 1 squared times epsilon 2 squared times a bunch of bounded stuff that would sort of contribute to the big O part, but they wouldn't. This is, this result is about what happens when these epsilon i's are small. So those the bounded factors just get absorbed in the big O. Okay, so sounds sort of good, but there are lots of issues. So one is that it's not literally true that the other coordinates have to be bounded. So you can have cylinders in your translation surface. So, so a cylinder is just a piece of the surface that looks like this. So, it looks like this strip where, and then so it has, it's foliated by these closed loops, since the top and bottom are identified, and then there's some other stuff in the surface we don't care so much about. So the point is that you can have one of these where the circumference, the length of the geodesic is short. So this could be like epsilon here, and so we want we're looking at the unit area locus. There's a 1 up here for the unit area. So this cylinder, you're not allowed to have it be sort of to be very long unless the circumference is very small. But if the circumference is epsilon, it could be the width of it could be 1 over epsilon, or maybe a little bit less because you need some area for the rest of the surface. But most of the area of the surface could come from this one cylinder, in which case you could have a situation like this. So this could be, maybe the epsilon is the S1 or something, but then you have this other coordinate like that his size is big if epsilon is small. 1 over epsilon would be big, and so that wouldn't, you might have to choose that as part of your basis, and it wouldn't be bounded. It turns out that this isn't such a big issue. I mean, this issue already comes up when you're just, say, computing the volume of the moduli space of tori. So like the simplest possible translation surface is just a flat torus, and then you're just looking at the whole moduli space, like the affine invariant manifolds, the whole moduli space. This issue comes up already, and you have to show that there you're just trying to show, well, one thing, even just the fineness of the volume is not so obvious. So you can already see it there. But the solution basically is that even though this 1 over epsilon is big, somehow you can arrange that so in this picture, say the circumference is purely imaginary. You can arrange that the cross direction has pretty small imaginary part. even though its real part could be big. So somehow it actually doesn't, even though its total length could be big, it doesn't contribute that much to the volume. So this is something, and to deal with this in this more complicated context, that you know, I mean, you could have lots of different cylinders and whatever. It's a bit more complicated, but I would say it's not the hardest part. So then the other issue is that so the measure is given sort of locally in terms of this linear subspace that it corresponds to M. So so you sort of know how to compute things, how to compute measure locally. So you use the period coordinates, which are local. But then if you want to sort of, you have to deal with the whole stratum to give an estimate like this, because, you know, well, this isn't just in one period coordinate chart that we're looking here. So you have to have enough period coordinate, but sort of the natural place to do the computation is in one period coordinate chart. But then if you want to cover the whole stratum, you have to use a lot of different period coordinate charts. And what you want to make sure is that you don't have to deal with infinitely many, because somehow you want to do the computation locally, and then you just want to add up finitely many things. And then, if you add up finitely many things that, of the same form, maybe the big O constant will get bigger, but you'll get the same sort of estimate. Whereas if you had to add up infinitely many things, even if each one of them was, so even if in each chart somehow things were good, if you had to use infinitely many charts, then you could have a problem. So this is kind of a major issue, and I'll talk about kind of how you deal with this. I'll focus on that. So there's going to be 3 issues, and 2 is the one I'll focus most on. And so then the third issue is you have to choose a basis for relative homology that's sort of adapted to short saddle connections. So you want to be able to see the short saddle connections from the basis that you're using. So that requires some work too, but as I said, I think the hardest part of among these 3 issues to overcome is 2. So I'm going to talk a little bit about dealing with issue 2. So what we want is we want to get some sort of finiteness of period coordinate charts. And so a natural idea is to use, the stratum itself is not compact, but we want to, because you can have surfaces with short saddle connections, and those give you divergent sequences. But we want to use a compactification of the stratum, so we sort of have an object that's compact that we can work with. So there's a whole family of, well, there's a whole zoo of different compactifications of strata that people have been working on, and there's a pretty sophisticated new one called the multi-scale compactification. And it's so it's actually compactification of the projectivized, the complex projectivized stratum. You don't want to compactify the whole stratum, well, because you have this, you can just have the area going to infinity or something, and that would be one way to diverge, and that's not so interesting. But so you could also look at the unit area locus, and this one you're also, when I write this P, I mean you're forgetting the direction too. It doesn't, the direction is not so relevant. I mean, it's not so important. So, so they use the letter capital Xi for this, just because it looks like different levels. So this is I mentioned the names: Bainbridge, Chen, Gruszewski, Gendron, and Muller. So This is sort of the second compactification that they've studied, but it has some very nice properties that are good for what we want to do. So, I mean, it's sort of a complicated object, so I'm not going to explain in detail what all the points are, but I'm just going to give you an example of a convergent, a sequence of things that diverge in the stratum but converge to something in this compactified stratum. So the picture, I'm going to use this sort of slit torus construction that I used in the first part for the E4 eigenform locus, but this is not going to be the E4 eigenform locus. So we're going to take a torus, let's say like 1 by 1. And then what we're going to do, so I'm going to describe kind of a family of surfaces. So we're going to take a slit here, A, B, and then we're going to take sort of a smaller torus that has a slit of the same length. And the sides are glued together so you can get between these two tori, they're connected. And just draw edge identifications. But this torus is going to be size, say, 2 epsilon by 2 epsilon, and the slit is going to be size epsilon. So you have this one piece that's staying bounded, and then so we're thinking about epsilon is going to 0. So we have one piece that's staying 1 by 1, and then it has this little slit and this little torus that's being glued into it. So maybe kind of a topological picture might kind of look something like this. So you have this part that's kind of bounded, and then you have this kind of small little part here. And the slit is something like there. So what should this converge to? So what you're supposed to do is you're supposed to think about kind of living in different parts of the surface. So if you're some green dude and you're living up here, you should think about what the world looks like to you. So basically, this smaller part of the surface, this 2 epsilon by 2 epsilon torus, is getting very, very small relative to you. You're staying maybe your size like 1/2 or something, and this other small torus is size 2 epsilon by 2 epsilon. So it looks like it's just sort of disappearing. So you record kind of from the perspective of this dude, what the world looks like is just basically this flat torus. It's 1 by 1 thing. But then the slit is kind of evaporated all to a point since it was size epsilon. And then you don't really see, I mean, the whole thing just kind of, this whole other torus just gets, just evaporates into that point. So if you're this green person, you don't really see anything in that point. You remember, say, a point where kind of everything disappeared into, it looks kind of like this kind of crazy point, but you can't really see anything about it. But somehow so you could just remember, you could say, okay, well, that's what it converges to. It converges so this would just be a single torus, one whole torus with one, say, kind of special point on it, one marked point. But since we want to sort of understand, I mean, so one of the issues is that, there's the short saddle connections in this case are sort of coming from the smaller surface. And so we've sort of forgotten how many there are. Like, maybe there's 2 independent short saddle connections or something like that, or 3 or something. Yeah, maybe yeah, so some number of them down there, and somehow, but it all gets evaporated at a point, so we can't see how many there were. So what we want to do is we also want to remember some information about the thing that's evaporating. So what we do is we think about now being this red person living on the smaller subsurface, and now this red person is size epsilon as well. So the red person is about the same size as the smaller torus, and so the red dude gets shrunk down as the smaller piece gets shrunk. So what does the world look like from the perspective of the red? So so there's this kind of, there's this 2 epsilon by 2 epsilon torus, and then there's still this slit. So like that. But then if you look sort of at the slit, so originally what you'd see is, you'd see into this other torus, which is bigger. But here, since this is 2 epsilon by 2 epsilon, the rest of it looks sort of infinitely big. So what actually you should think about is this slit is glued into this whole kind of infinite plane. So really, it's like a copy of C. I'll just kind of shade it in so that first. So there's AB, and then so sorry. So I'm just kind of shading it to note that this whole copy of C is kind of part of the translation service, and then you also have this stuff here. So in terms of what differentials, in terms of the holomorphic one forms, this isn't a holomorphic one form, it's actually a meromorphic one form, because it looks like the one form dz on the complex plane, but you're supposed to think about the extended complex plane, and so the one form dz has a double pole at infinity in C, and that so it's sort of this, represents that it has infinite area, and there's so it's not a holomorphic one form. But you can still do sort of a lot of flat geometry with these meromorphic differentials. So it's sort of like a translation service, but it's some parts of them are not like polygons. They're sort of like half planes or full planes, or sometimes you can glue together, say, 4 half planes and get something more complicated. So somehow you don't so from the red person's perspective, you don't remember any of the shape of this torus upstairs. So I mean, the torus could have slanted a little bit, but you sort of forget that information. You just remember that there's this infinite amount of space there. So really, the topological picture looks kind of like, so you have this torus here with a marked point, and then there's sort of a separate piece of the limit. So if this is like x epsilon here, this would be x bar here, the limit, or maybe, as epsilon goes to 0. And then this is also a torus, but it has a pole, double pole at that point. So this compactification, it remembers sort of a lot of information. So it remembers kind of the shape of pieces that are staying bounded, but also remembers the shape of pieces that are getting very small. So you still remember, for instance, that the limit contains information about the shape of this smaller torus. So if you did a slightly slanted flat torus on the bottom, you'd get a different limit point. So both of these have differentials on them that record that information. Okay, so that's what this compactification is, and so it has some nice. Well, okay, so I gave you an example. So there's more complicated things. You can have a limit of, you have cylinders that are getting, like we had this example up here, that also converges to some limit. It corresponds to differentials with simple poles rather than double poles. And there's a lot of other different phenomena there's a lot of rich kind of stuff in the boundary. But I just want to tell you some properties of the compactification. So so as suggested by the name, it's a compact topological space. So we'll be able to use compactness arguments. It's a smooth, so it's actually a very nice topological space. So it's a smooth complex orbifold. So it's almost as good as a complex manifold. So it's not very singular, and so it also So when I say complex orbital, I mean the complex structure. The strata naturally has a complex structure, and it extends. The complex structure extends to this compactification. And there's a particular, and then there's nice coordinates, orbital coordinate given by the coordinates are sort of given by the analytic plumbing construction, which allows you to sort of give coordinates near a nodal Riemann surface. So underlying any point in the compactification is an underlying Riemann surface, which could be nodal. So things like plumbing, which is a way of opening up a node, are relevant. And so it's very nice to these. So it's not just that abstractly it's a smooth complex orbital, but also it has this nice system of coordinates that you can understand and use to tell you about surfaces nearby. Yeah, maybe I'll just stay with nice coordinates. And then the third property that's nice is that it's a sort of a big compactification in the sense that there's a lot of different boundary points, and sort of a consequence of that is that so a neighborhood of X bar, some boundary point, is small in the sense that there aren't so many surfaces in it. So basically the compactification remembers more information about sequences that converge to a boundary point, so there are fewer types of sequences nearby that converge to that boundary point, which is good because there are fewer types of translation surfaces near a particular boundary point that we have to worry about. So if we just remember kind of this top part of the surface where what the green person can see, that would be sort of a smaller compactification than the neighborhoods there. You could have any shape of flat torus on the bottom part, and the corresponding sequence x epsilon would still converge to the same boundary point. So you'd be sort of losing information, and so there'd be more surfaces nearby that you'd have to deal with. Okay, so those are some properties of this, and so now I want to give you, so this is kind of one of the main tool, and I want to give you now the proof outline of the theorem. So basically, how do we implement this heuristic that we were talking about there? Of the main theorem. Okay, so the first step is to reduce to sort of a local computation near the boundary. So by compactness of the multi-scale compactification, it suffices to prove the big O estimate in a neighborhood of each boundary point. X bar. So the sort of picture looks like you have kind of the boundary here. So this is the boundary of the compactification. It's the boundary of the smooth part. So this here is just the projectivized stratum, and then on its boundary is some point X bar, and then so you want to do things. So if you can pick some neighborhood U and you can prove the estimate there, then you can just, by compactness, you can cover kind of a whole neighborhood of the boundary by finitely many things, finitely many neighborhoods. And then the statement is sort of trivial away from that neighborhood because the statement is only has content when you do have some short saddle connections. And if you have some short saddle connection, then you have to be close to the boundary. So if you prove it in each one of these, then you can just add up all the estimates that you get, and you get the same form of an estimate for the whole thing. And then it's trivial kind of away from the boundary. So we really just have to worry about a particular boundary point and its neighborhood. Okay, so because this multi-scale compactification is a big compactification, this U should be limited what types of surfaces there are in it. But actually, we have to divide up U further, but it'll just be into finitely many pieces. But we divide U into finitely many pieces, V1 up to Vn, and we want each with each Vi like actually a period coordinate chart. So which means that you actually have the periods. So if you pick some basis for relative homology, the periods give you kind of a description of all the surfaces in that VI. And so, so there's sort of two parts of that, which is that if you can pick any so there's sort of an injectivity and surjectivity. Maybe I won't get so deep into that, but so basically these VIs are the sort of thing that you can do like a volume computation with, because you're actually just, in that VI, it just looks like the stratum just looks like a linear space. And so this part is one of the hardest parts of the proof, is dividing U up into these pieces and proving that each VI is actually a period coordinate chart. And so it involves really using these plumbing coordinates and some delicate arguments. Okay, so then step 3 is so we have some picture like this. We only have to worry about this one X bar, and we only need to look in a small neighborhood U around it, and then we've divided up this neighborhood into these pieces VI. We have, say, so VI here. And then, so the first two things, we didn't talk about the affine invariant manifold M, or the measure, the support of the measure mu at all. The mu didn't come into this. So now we need to deal with that. So the M, the support, is some affine invariant manifold. So it could intersect this. And so the picture that we really worry that we have to rule out that would be bad is if you have this kind of infinite sort of winding around like this. So M locally looks nice because away from the boundary, it looks nice because it's just, it basically looks like a linear subspace. It could be actually a union of a couple of finitely many, but basically it looks just like a linear subspace. So it's very nice locally away from the boundary, but it could sort of accumulated on the boundary in a weird way. And in particular, a priori, it seems like it could intersect. So this is M could intersect VI kind of in a nasty way in these, say, infinitely many components. We want to rule that out. So what we want is that M intersects each VI nicely. I'll say what that means, but so yeah, infinitely many components. So we want to rule out this picture. So the observation is that if this was like an algebraic geometry conference, you wouldn't have pictures like this if everything in sight was an object that naturally came up in algebraic geometry. So if everything was a variety or something like that, then with varieties, you don't have this kind of, two varieties intersecting in infinitely many components. That's just something that doesn't happen. So what we want to do is we want to do everything kind of algebraically. So we want to choose the VI. So we're interested in the M intersect VI. So sorry, M intersects up here, intersects VI nicely. So we want to choose VI to be, so the VI will be sort of like, it's not going to be itself actually a variety, because kind of you're sort of dividing something up into kind of these finely many pieces, and there's not really a way of doing it with just kind of, you know, polynomial equations or analytic equations, but you can use, you kind of want to do things like the type of things that you have to do to get these VI, or you say like the angle of some complex numbers in some interval. So those aren't sort of complex algebraic conditions, but you can make VI be what's called a semi-analytic set. So there's an analytic structure on this compactification, and what that, so semi-analytic means that VI should be cut out by analytic equations and also analytic inequalities, real analytic equations and real analytic inequalities. So saying like the angle of some complex number is something that you can phrase in terms of an inequality on some real analytic function. So that's one part, but then we also need M to be kind of nice. So we want M. So how do we know that M lives in this kind of, is sort of is an object of algebraic geometry? So this is follows from a deep theorem of Simeon Philip. So M is a quasi-projective subvariety of the stratum, which is not, so that's sort of it's clear that M is basically a complex manifold, a complex orbifold of, complex suborbifold of the stratum, but somehow the algebraicity is sort of about what's happening at infinity in some compactification. And so this doesn't follow at all, obviously, from the fact that it's sort of linear in these period coordinates. Part of the problem is that the period coordinates don't extend to coordinates to the boundary. So this coordinate system that I mentioned above here, it's sort of related to period coordinates, but there's some extra stuff because not all the period coordinates extend to the boundary. So we've sort of established this whole picture as living in kind of algebraic geometry land. So VI and M are either semi-analytic or actually algebraic, and then so this implies that M intersect VI has finally many components. So it's fairly standard. So if you have two semi-analytic sets, and an algebraic variety is a particular type of semi-analytic set, so any semi-analytic set has finally many components. And an intersection of two semi-analytic sets is semi-analytic. So we've ruled out this picture. So basically, M will look like some finite union of components. The picture will be maybe something like, we sort of want to look at a boundary point where M actually converges to that boundary point. So maybe it'll look something like this, and you'll have some branch there. Then M will kind of go around and do something, and there'll be some other branch, but there aren't sort of infinitely many branches. Okay, so that's good. So we've controlled kind of how M looks in some sense near the boundary. And then now we want to say that, so each, and this isn't hard, but so once you know all this, so each component of M intersect VI, and we know there are finally many of these, but each component of this is a single subspace in period coordinates. So each VI we said is a period coordinate chart, and so there's a linear structure on the whole VI, and M is just it's just a linear subspace. We can call it W and V. So now basically we've kind of gotten to a point where we can sort of implement this heuristic, and that's the idea. So now really what we have is we just have a single linear subspace. We don't have to worry about, you know, the global nature of M anymore. We've kind of used the fact that M is locally linear, and we've kind of done all this stuff with the boundary to get that even near the boundary we can just sort of, we can think of it as basically like a single linear subspace, or finally many linear subspaces. And so now we implement the heuristic for this W. So we think about so we have to do the other two parts. We have to deal with the cylinders, and we have to deal with choosing the bases correctly, which take work, but you sort of know where to go once you have for this W. So once you have this situation where you just have to worry about a single linear subspace, you're in good shape. Okay, so that's the outline of the proof. Thank you for watching.